for Malena's talk, which will be on iteratively weighted flexible Krylov methods for inverse problems. Malena.
Can you see my screen okay?
I can see a screen and hear you. Perfect. Thank you.
Okay, perfect. So yeah, first of all, thank you very much for having me here. It's really a pleasure to be able to introduce myself in the hub. Even if I haven't started working there, I will start in June. First of all, I want to say that I'm actually really impressed about the last talks we've been having. I think like the quality is amazing, like the range of topics. Like, I'm actually very impressed, and I'm very inspired as well about the like broad range of big topics and data sets that I would be able to work with, hopefully in the next months. I'm going to give you a little spoiler, and I just want to apologize already. This talk is going to be a bit more technical. It's pretty much a linear algebra talk, so there will not be you know, all the really nice images we've been seeing so far, but hopefully I'll be able to convey some of the work I've been doing, what I did actually in the University of Bath and in a research I did at Emory University a couple of years ago, and hopefully be able to convey some of the ideas that we discussed, and maybe justify as well how they can be applied as well in the imaging and related to healthcare setting. Actually, I have not worked with real data with these specific algorithms, but I know there's some universities that are already developing it in a more like applied way. So I know, for example, the Beijing University of Technology has applied some really similar algorithms to electrocardiography. So yeah, again, I do feel a bit like the black sheep of this workshop. You've all been presenting all these really amazing problems, very complicated, with like a lot of like different layers of complications. And I'm just basically going to try to explain to you why I'm trying to solve AX equals B, which, you know, in theory should be the easiest problem you could solve. But of course, we're talking about an inverse problem setting. So my AX equals B just come from even if it's a linear problem, it comes from a suitable discretization of Fredholm integral of the first kind. So I will assume I know my linear operator and I do know my measurements, and I want to reconstruct the data that generated those measurements. So just to give you an idea what kind of problems rely on or fall into this setting, you can think about image deblurring. That's usually the easiest problem to think about, and usually the one I have in mind when I'm thinking about these kind of problems. I do have a PSF, which is basically a function that tells you how a single pixel of light gets spread around in an image. And then I have a convolution with this between this PSF and an exact image. And if I add some noise,
can I just check? Sorry. Are you changing your slides? Because we can only see the first slide so far.
Oh, okay. Which slides can you see?
At the moment, I can just see your title slide.
Yeah, I was actually changing them.
Okay.
So yeah, sorry, I was just talking about this problem. So I'm just like solving AX equals B, but my B has some noise added in the measurements. And this was the slide I was talking about, really. So when I think about these sort of problems, I usually have in mind an image deblurring problem, just because it's the easiest one. So I usually have something that looks like a PSF, which if you think about a pixel that it's been like painted just in the middle of this square, this would be the image of this single pixel after it's been convolved with this PSF. So you can think, for example, that you're taking a photograph, but you're just kind of like shaking. And then you have like some noise added, and then you get some available image. And for simplicity, I will just assume now that I have this PSF. But again, you can use similar techniques to the ones I'm going to talk about, in which you also try to recover this PSF when you don't know how it looks like. Or if you want something more applied on the medical healthcare setting, you can think about some tomography reconstruction. So basically anything I care about is any linear measurement of an exact phantom that's been convoluted with some noise, and I get some available sinogram. So why are these problems hard? So again, is AX equals B? Why is it so hard? Well, I mean, even if it's linear, these problems are really large scale. They are inverse problems, so they're ill-posed. So all the matrix A inherits a lot of we'll say bad properties or ill-posed properties from the original problem, so that if I just try to solve this problem very naively without assuming any prior information about the problem at all, and I just try to invert A in some way, and just multiply it by the vector measurements, I just get something that's very contaminated by noise. So for example, in the blurring problem that I was showing before, if I had this blurred and noisy image and I want to recover the reconstruction just by inverting A, I just get basically pure noise. So I'm just going to explain what Krylov methods are and how they're used in inverse problems. And then I'm just going to introduce some more advanced Krylov methods that are used for, again, more advanced regularization problems. So let's start with something very simple. Maybe you've heard about Tikhonov regularization. Is one of the simplest ways that we have to add some regularization to our linear inverse problem. One nice trick is that if you have a regularization matrix, so here we're just basically penalizing everything that's in the range of this L. So trying to penalize the unwanted properties of our solution. We can also rethink about this problem as, okay, we'll just do a change of variables, and now our L appears on the other side. So somehow this L is shaping the way we're generating our solution. So this inverse of L is also related to properties that we do want in our solution. So again, this links a bit to the machine learning idea of having generators, or learning generators or learning regularization terms for our solution. And hopefully this kind of very simple example, if you want, will give you an idea of how this really affects the way that we seek a solution to our inverse problem. And in my specific case, I will talk about Krylov subspace methods. So what is a Krylov subspace method? Basically, it's a projection method. So again, we're talking about very large scale problems. So usually we cannot even access our operator A. We can just have things like matrix vector products with this A, but it's so large scale that we cannot invert it directly. So what we try to do is to project this really big problem into a smaller subspace and solve it in that smaller subspace. And then we keep increasing the dimension of this subspace, and then we keep getting a better approximation of the solution of the high dimensional problem. In particular, Krylov subspaces and spaces that have this form here. So basically, you can think about just taking one vector and taking one matrix and then multiplying the matrix several times with a vector, and that gives you different basis vectors for your Krylov subspace. And again, this Krylov subspace is a subspace that increases at iteration. So at iteration k, it will have k basis vectors that are linearly independent. And we want to find a solution that lives in one of these Krylov subspaces, and we will impose some optimality conditions by imposing some conditions that are residual. So we wanted to minimize AX minus B, we say the least squares AX minus B. So we impose that this residual is orthogonal to another Krylov subspace. So the most common Krylov subspaces are GMRES and LSQR. LSQR is mathematically equivalent to CGLS, which you might be more familiar with. And they have this really, really basic way of working. So if we just start with our Tikhonov problem, which again, now for simplicity, we'll forget the regularization matrix because we can, as I was saying before, we can just do some change of variables. And again, this lambda could be 0 if we just want to recover the original least squares problem. And then at each iteration of my iterative algorithm, I will expand my Krylov subspace. So my Krylov subspace starts with one basis vector, and I keep adding basis vectors as soon as the iterations proceed. And I update a partial decomposition of A that has this form. So basically that just to facilitate or to allow for the projection step to be cheap or to be done. And what I want to do is I want to consider my solution to belong to the Krylov subspace. The Krylov subspace is spanned by the columns of this matrix V. So then I write my solution as a linear combination of these columns. And what I do is basically I just take the original problem that I had here, and then I substitute here inside, and I get this really nice projected problem. So before I had to solve something that was like in Rn, which n could be like very high dimensional, and now K is it just goes with iteration. So like if we stop early enough, that's going to be much, much cheaper. So one particular property of Krylov subspace methods, which makes it really good and really suitable for inverse problems, is that you can basically just start with your original least squares problems, and then you can regularize it, like let's say with some Tikhonov regularization, and then you can project it to obtain your solution. Or you could go the other way around, and you could, in theory, just first project your original least squares problem, and then add some regularization to the projected problem, and then you would obtain the same thing. So again, this holds when lambda is fixed, so when this regularization parameter is fixed. There's a bit more work to do understanding what happens when lambda is chosen differently at each iteration. But I think this gives an idea of why these things are so interesting, or why they're interesting to me at least, which is thinking that if I have a big problem and I add some regularization that is suited for that big dimensional problem, or if I project it into a smaller setting and then I find a regularization that is good for that projected setting, in some cases those two things are equivalent. And again, I can just do a projection step. That's very, very, very cheap to solve. So if we want something slightly more complicated, we can think about some more advanced regularization terms, which, for example, we could use some like p-norm regularization, or some TB. These are usually sparsity enforcing terms, in the sense that if you just think about, for example, like just take the p-norm first. If we were taking the zero pseudo, like zero norm, like it's not a norm at all, it would just like trying to count how many elements of my object are non-zero, and we'd penalize that number. We're definitely enforcing our solution to have a small number of elements that are non-zero. So that's NP hard, so we cannot solve that. So we relax that a bit, and then we can find different ways of choosing P. If P is smaller than 1, this is not going to be convex. So again, we fall a bit into the problem of, do we know we're converting to the right solution? So usually we just decide to take P equals to 1. And again, with TB, total variation regularization, what it does is trying to find things that have sparsity in the gradients. So if you think about some piecewise constant solution, or in smoothwise constant, if you want, you can trick this to think, if I have like a small number of jumps in my solution, I can just penalize the number of jumps instead of penalizing the number of non-zero elements of my solution. And we can rewrite this just using some basic linear algebra tricks as some weighted two norms where the weight depends on x. And the trick that I would use in this case is that if we have an approximation of x that is good enough, we could just use these weights applied to the approximation of x that we already have. And same applies for total variation. So we will have an iterative method. As I was saying before, I just solve a problem at each iteration. So at each iteration, I get an improved version of the approximation of x. So I could just, in theory, have a sequence of problems where my weighting matrix is changed at each iteration because I get a better solution of x, and I can apply the weights to that better approximation. And the way I would solve that, again, is using Krylov subspace methods. But in this case, things get slightly more complicated because I have these weights that depend on the iteration. But it doesn't really matter. You have like a very similar setting in which now my weights are going to be, like as I was saying, like one of the first slides, you can just like transform that into standard form. So this guy, you do a change of variables, and these guys here multiply like the inverse of these guys multiply on this side, and then you get some preconditioned space. So again, the projection system is very similar, but now your space incorporates these weights in the basis vectors. And I'm always very excited about this slide. Even if it looks quite simple, I just have this exact image that I want to, or not image, signal that I want to reconstruct, and I have this corrupted version of it. And these are like different methods that have been used, but basically I'm just showing the basis vectors that you would use with each of the methods to reconstruct your signal. So this is the classic GMRes, and you can see that these basis vectors are extremely oscillating. So it's very hard to recover an image that looks piecewise constant if I have some basis vectors that look like that. And again, if you think about the machine learning context, like you really want your generator to have, you know, the right properties. You want the generator to be able to reproduce images that look like your right image. So this is kind of like the simplest version of it. Like I'm just doing a linear combination of things, and these things don't look at all like my original image. So it's going to be very hard for this method to convert to something that looks like the original image. And then we do different things, and especially this is the method we were developing, you can really see how the basis vectors really start reflecting much better the behavior, like the intrinsic behavior of this exact image. And again, this is just projection step, same than I had before, just my, my partial decomposition of A now is a bit more complicated, and I have my weights entering the space. I think I have to summarize quickly, but one of the problems that we have in this setting is that the really nice property that we had before, in which finding a good regularization for the high dimensional problem is the same that finding a good regularization in the projected problem, doesn't hold anymore. And even if doing some experiments, you can see that in practice, it doesn't make a big difference if I'm trying to find a regularization for the high dimensional problem, which I don't know how to solve. It's so big, I cannot even like handle it. Or if I do things in the projected version, they give similar results, but they're not the same thing. So it's quite hard to know where the problem will be converging, or what's the solution I will be converging to if I apply the regularization just on the projected problem. And the things that we should be thinking about instead is like, can I approximate a good regularization for the high dimensional problem in my projected problem? Just very quickly, this is the fanciest picture I have. You can probably see it's maybe not as high tech as the one we've been seeing in the talks before, but just I'm doing an X-ray tomography reconstruction of this, you know, very slightly fake toy example. I have a sinogram and I want to reconstruct the exact image. And these are just some error plots that basically show that if you compare with like other standard techniques like sparse size, like a soft thresholding algorithm or FISTA, our method basically converges as quickly or like even quicker, and like to some very similar error norm levels. So just to give a quick summary, I think flexible Krylov transmitters can be used to compute sparse solutions. Well, we've proven that can be used. They have a very nice generalizable framework that has some good theoretical guarantees. And those are just very classical techniques yet still. But I think that these kind of methods open the door to way more advanced regularization terms, and hopefully also some more data-driven methods that maybe can be used in combination with flexible Krylov methods, or maybe just other ideas. But I think that the works done in this very classical setting give you an insight on how regularization and finding a good space for solution are related to each other. And I think they have a lot of kind of heuristics to exploit in these new methods that we will probably be developing soon. That's pretty much everything I want to say.
Brilliant. Thank you very much, Malena. Do we have questions for Malena? If not, I have one, which is, in some ways, can you not see Krylov methods as a sort of regularization? I mean, it's in the sense of you're building a basis, and that basis is small, and that's sort of regularizing the data down. So in some sense, you've got two different regularization methods coming to
Yes.
into play against, well, not necessarily against each other, but together in order to give you the overall regularization. Is that
Mhm.
a helpful way to think about it, or are they so different that in actual fact?
No, it's definitely a helpful way to think about it. And I actually had done some work about it as well, which it's quite nice to see how they interplay together, actually. How just using Krylov methods or just using some more classic variational methods give you similar results in a way, but they take longer while if you use them in combination. Like you can find like a sweet spot. You know, as always, the more information you have about the problem, the easier it is to find a sweet spot. But you can find some really nice convergence properties when you use the interaction, actually. But it's definitely a really good way of thinking about it.
Brilliant, thank you. Any other questions for Malena? If not, let's thank Malena again for a really excellent talk. And again, thank all the speakers in this session. It's been really good to see the real breadth of things that are going on across the centre, from mathematical, machine learning, and clinical methods, taking those mathematical and statistical techniques into account.